Matrices aren't just arrays of numbers, they are functions. Today we aren't going to learn about matrices. We're going to discover them. When I say the word function, what do you think of? You probably think of a machine which takes in a number x and outputs a number y. For example, y equals 3x. Now, how about multiple inputs? Can a function have multiple inputs, and would that even be useful? Well, of course. A lot of the time, a scenario depends on more than one factor. Just a measly single input isn't going to capture the whole situation. So it's actually quite common to have functions with multiple inputs. For example, x1 and x2, and then it outputs a number y. And in general, we can have as many inputs as we want. But here's the crazy question. Is it possible to return multiple outputs for a given input? In a lot of situations, there isn't just one variable at play, and if you want to model that scenario, there are several quantities you care about. It's not actually uncommon to have a function return multiple numbers. Now, obviously you're thinking, how is that even going to work? A function can't return multiple outputs for a single input, right? That's true. A function always returns one thing for a given input. The trick is that one thing itself can contain multiple numbers. We just bundle all the outputs into an ordered list. For example, we can have y1 and y2 as an ordered pair. It's a single object, but it just has two numbers in it. So even though the function is giving us multiple numbers at once, it's still legally a function. It's just one output that holds all the information we care about. So this is going to be really important. We want to generalize this so you can actually have functions which take in n numbers and output m numbers. M does not have to be equal to n. We can say such a function is from Rn to Rm. That means it takes in any ordered list of n real numbers and outputs something which is an ordered list of m real numbers. Now we have functions from vectors to vectors, but you might wonder, which functions are the nice ones? I mean predictable and easy to work with. What does predictable mean? Well, vectors have two main operations, okay? You can add vectors and you can scale them. Now, it makes sense that a function which respects the structure of vectors shouldn't interfere with these operations of adding and scaling. So basically, if I add inputs and take the function of the result, that should be the same as taking the function of each of them and adding. Similarly, if I scale an input, that should be the same as scaling the output. Now let's take a look at a special case R2 to R2, and suppose we have a function with these nice properties. Now I wonder, can we find a formula of some sort for f of x? Okay, well let's try. We'll take an arbitrary vector, x1, x2. But how do we even start with this? Well, in math, it helps a lot to write stuff in different forms, so that's what we're going to do. This is the column vector form, but we can write it in a different form, and you might know what it is, using the I and j vectors, where I equals 1, 0 and j equals 0, 1. Well, now what? Well, we know these nice properties of f, so we just apply them. We can split it up as a sum, and we can take x1 and x2 out of the function, because they're just numbers. Okay, well, now what? Note that f of I and f of j, they're just vectors, okay? Because f takes in a 2D vector and outputs a 2D vector. So we'll just let them be AC and BD. And well, now we have a formula. Notice something. This function depends only on these four numbers, A, B, C, and D. Once we know those numbers, we can compute the output for any input. So these numbers are the most important part of the function. They literally define it. Look at what just happened. Each entry of the output is just x1 times something plus x2 times something. And that something is just a number. Now this idea is actually pretty important. We call it a linear combination. A linear combination of things is just a sum of scaled multiples of those things. So you just scale those things and add them together. And this is going to come up a lot. You can even have linear combinations of vectors. So now we showed this idea for R2 to R2, but you can do this more generally to show it for Rn to Rm. And you get something like this, where these numbers aij are just specific numbers which really define the function. This is really cool because it shows us if you have a function which takes in n d vectors and outputs m d vectors, and it has those two nice properties, then it has to end up looking something like this, which basically has a sort of array structure in these numbers aij. We could write f of x as usual, But then you have to look at the definition of f to see those numbers. Instead, I'm going to propose a very interesting notation. We're going to put the numbers right in the notation of f itself. Okay, hear me out. So this grid of numbers is the function itself. The idea is we can use a grid of numbers to represent a function. Okay, so maybe we call this grid of numbers A for array. Or maybe it's just because A is the first letter of the alphabet.
Bruh.
Then if it has n columns, notice that that means it has n input numbers. And if it has m rows, then it has m output numbers. So just take a moment to think why that's the case. Now, if we want to describe the size of the matrix, we usually say m by n, where we say the number of rows first. So this one has m rows. Okay, but that means also the function is from Rn to Rm. Yeah, I know the order's switched, it's a bit annoying. Okay, so just so you're on the same page as me, I'm saying that an m by n matrix is an array of numbers, but it acts as a function from n variables to m variables. And it has really nice linear properties. By linear, I mean it has those nice properties of addition and scaling. Okay, now let's analyze this new matrix function thing that we've discovered. So we can analyze a grid of numbers in 3 different ways, right? Rows, columns, and, well, each entry. We'll try to find a formula for the ith entry of ax in terms of a and x. By the way, when I say ax, you can kind of think of it as a of x, like a function, where x is the input. And we're using this x notation to mean the whole vector x1, x2, all the way up to xn. Column-wise, we'll try to find a formula for ax in terms of the columns of A. If you're learning matrices or linear algebra for the first time, I really suggest you try these yourself. It's much better for you to discover this by yourself than me having to give it to you. Okay, but either way, I'm just going to show you how it works. So, how does each row of A appear in the output AX? Well, let's look at row 1. As a vector, it looks like this, right? But how does it appear in AX? Well, it appears in a sort of weird way. It appears like as the sum of the entries of this row, but with x's being multiplied, and then you add them together. It's a bit weird, right? But where have you seen this idea before? Well, if I show the x vector, maybe you'll realize what it is. This is actually a dot product. If you take the dot product of these 2 vectors, that's the same as taking the sum of the products of each entry. And that literally is this. So the ith entry of ax is the ith row of A dotted with the vector x. This might seem surprising, but in reality, the idea of a dot product of lists of numbers is quite similar to an idea of linear combinations of those numbers. Now, entry-wise, I just want a way to describe in words how the entries of A appear in AX. It won't be a formula, but we just want to put it into words. So let's look at the m1th entry, for example. It's in the mth entry of AX, and it's the coefficient of x1. So obviously we can just generalize this. The ijth entry of A would be the coefficient of xj in the ith entry of AX. Okay, that's a good way to describe it, I think. Now let's look at the column-wise interpretation. So we can see intuitively that the jth column of A is like the column of coefficients of xj in AX. If that makes sense? So you saw this idea before. We can write this vector, this output vector AX, as a sum of vectors and take the x's out of each vector, giving this. So AX is a linear combination of the columns of A. This is extremely powerful. The columns of A are really more important than you might have expected. So you can check this for yourself, that any function in this form, this matrix form, automatically satisfies those 2 nice properties we discussed. What we've shown before is if you have a function with the properties, then you can write it in terms of a matrix. We didn't really show the other direction, but you guys can do it for yourself. It's not too difficult. So the main takeaway from this video is that a matrix is a grid of numbers, but it can act as a function from n variables to m variables with some nice linear properties. And also these 3 things about the row, entry, and column interpretations of the function, these are really important. So next time you see a matrix, remember, it's not just a grid of numbers, it's a function.